So the first example is 11.9.1. So this S is defined as we start from 1, right? A squared plus A squared. Okay, so this is not exactly the form that we just derived. It's not from negative infinity to infinity. So the first thing you want to do is to change this to minus n, also add it to minus n. So one easy way to do is just a change of variable. So we can say we call n your minus n, just say n change to minus n, right? And so this become n squared, just m squared, just become m squared. The m becomes minus 1 to minus infinity, right? So you can say that the same thing changed to from minus infinity to 1, because you change sum from minus 1 to minus infinity is exactly the same as just minus infinity to minus 1, right? And now you originally just change m to n, but then you can call it back to n, because n is just a summation variable. You can call it whatever you want. You can call it also n also, right? Then change back the expression is exactly the same. The s and s. S is this one. Now you show that it's equal to this one with negative integer. Now you can add the 2. When you add the 2 to s, will be from negative infinity to minus 1, and then 1 to infinity, right? This means you're missing one term, missing the n equals 0 term, right? So all you need to do is add that term and then subtract back that term, right? Right. So you can say this n from minus infinity to infinity, n squared plus a squared, and then minus this n equals 0 term, which means that minus n equals a squared. Now this one you can use the method, right? This one you can just use the method what we just did, and once you calculate that, you can solve as using this equation. It's okay. So that's how you just deal with the situation when the summation is not exactly corresponding to the formula. Now you apply the formula. So consider just this one and use the formula. Just the first line of the table. So minus this one is equals to minus the sum of the residue of f, which is now becomes a 1 over z squared plus a squared times pi cotangent of mc. The sum of residue of f, right? Which is this one. Now, what are the location of residue? Yeah, plus or minus I A, right? I times A. So, and those are simple pole, obviously. And so you have two terms. So, would be easy. So, like if it's pi A, you multiply Z minus pi A, then the rest is the rest of the in the denominator is Z plus IA, and then you evaluate at Z equals IA, so it's 2IA denominator, and then pi times the tangent of pi IA. So the first residue, this the negative sign is from here, so negative. The second one is at minus pi A, pi RA, and then the denominator you multiply Z plus IA, cancel that, and evaluate Z equal to minus IA. The other is minus 2 IA, right? And the cotangent is an odd function, right? So you change the negative sign, you change, you get a negative sign. So you can get rid of that with one of the negative sign, right? And then the two will be the same, right? And then you just basically cancel, get rid of one term, and then change it to right. Right? And now you can use the, if you want, you can use the property of the Euler relation to change cotangent to maybe that will give you the hyperbolic cotangent. Let's see what the text will get. This is the first example, right? And it would turn out to be cotangent of cotangent. So there's an X here, right? So that would be pi. I mean, this is elementary, so you know how to do it. Just use the Euler relations with the cosine and sine, and substitute imaginary argument and change it. That becomes all the exponential function becomes has real argument. Then you can use the cos function and sinh function becomes cos and sinh. Then the ratio becomes cos. Hyperbolic cotangent is really difficult to say. And that is it. Divided by 2a. Divided by a, that's a. Okay. So this is this one, right? So you minus a squared divided by 2, so that will give you the final answer. Is that okay? So, say that again. Yeah. F is this. This is F, right? This is F. F is the from the formula. So the formula is you look at the table, sum over F Fn. The formula is that I mean hit this one. You want the sum over Fn. But this is your F as a function n. Okay. Just call this expression as a function. So you want to sum over this one. You want this series, right? You want to sum this series, and the each term has the expression of 1 over n squared plus a squared, and we call that f. We just give it a name. That's that's the previous. That's what we did before to divide this formula. The formulas in the table is what at least the first line we divide that. We multiply by that, and integrating over the big circle, all the residue coming from the cotangent will give you this this sum, and then the rest of the residue will be here, will be the rest of the formula. This one. This is evaluate the residue at the poles of F. Okay, and that's using the residue, all the residues from the big circle within the big circle. That's how we divide this formula. Okay, that's a derivation, but once we have the derivation, you can just use the formula. So the table 11.2 are the formula that we derive from the residue theorem. So once we are convinced, we convince ourselves that these are correct formula, we can just use the formula. Okay, and so this example is show you how to use the formula, right? To deal with the subtlety that the sum is not from the whole range of integers. So what we did is just to manipulate it to get to a sum of the whole, all the positive integer. So this sum s now satisfy this equation 2s plus this sum minus the zero, n equals 0 term equals to, I mean, this equals to that. So, but this sum, we can use the formula. And use the formula, you get that. Okay? Then you use this equation to solve for s. Is that okay? So, pi c, This one, this is just the formula. Just we start out using that and then divide that formula. Once we divide that formula, that is within the formula. That's just yeah.
That's just in the book, right? That cotangent IZ.
Yeah,
Yeah.
that's in the
So
book.
you just basically take that. Just, I mean,
Well, they take that from the book, but then we divide it.
yeah, I mean,
Yeah, yeah,
and you're doing the problem
yeah, yeah.
Yeah.
Once you finish
just want-
derivation, then you just you convince those are correct formulas. You can just use those formulas. Yeah. Okay. Are you? So we went through the derivation of this formula before. Are you having questions with the form, the derivation? Yeah. So this is how we divide that formula. Once we divide that, we just use that formula. Okay, this is how we use that formula. The formula in listed in the first line of 11.2. This is what we are using. Well, for our class, you don't need to memorize because everything is open book. Even the exam, you have so most likely the take-home exam, which is open book. We don't need the formula. But for unfortunately for our PhD student taking the course, but hopefully not one of these questions. If you actually someone just asks you, then if you forget the formula, just go through that. You want we derive it again, okay? Just try to. I mean, sometimes memorizing formulas are more difficult than memorizing the concept. So you remember the concept and you just spend some time to re-derive it again. That's okay.